Okay, so this is a video sharing service. And by video sharing, are you thinking of something like YouTube or TikTok, or I guess it doesn't, okay, like YouTube, sure. Right, so the user interface can just be let's assume the user interface is like pretty similar to YouTube, and let's not spend time on the UI right now. But because it's what's interesting about this is dealing with the storage and yeah, different kinds of requests on the back end, I think. So we're going to have the browser here. The user is going to interact with this service through a browser, right? And although there might also be mobile apps, so there could also be there might be an iOS app and there might be an Android app. And these are going to run, these are going to have to make requests to some kind of backend and to do things like searches and to play video data. Okay, so there might be some kind of, let's just call it the API, just to give it a very generic term, very generic name. We start off with a very simple design. We have some kind of JavaScript app running in the browser that makes requests to the API. And we also might have requests directly to the web page to get the different pages of static HTML. Those might be served by a different web server that generates the pages for the static pages for the site. Once you get back, if you get back some HTML and that includes some JavaScript, that JavaScript application might actually interact with a different domain. These are different domains and they're different. So in order for clients to contact two different services, they have to be using different domains. So this might be youtube.com up here. And this one here might be api.youtube.com. Okay. And my guess is you also want to have a CDN here for a different domain, which is, let's say, vid.youtube.com. This is for the video content. Yeah. And actually, you might also have a CDN in front of your web server just to cache the static pages that might be the same. Okay, so the clients are going to contact either 2 or 3 different services. The browser will contact youtube.com, and then the native apps as well as the JavaScript app running in the browser will contact this API domain, which handles things like search and leaving comments and stuff like that. And these apps will also be fetching video data from a different domain, and I'm doing it. Having those requests go to a different service because that type of data is very different, and I'm going to have a different kind of architecture for supporting it. Okay, but there's a CDN in front of it, in front of this video. Data. Anyway, so the videos themselves are probably going to be stored in some kind of distributed file system. If I was implementing it myself, I might use S3. So this is, or another distributed file system. Okay, so every video will be stored as a file in this file system. S3 provides optionally like an HTTP interface for public users to download data, to download the files if you configure the files to be publicly readable. And you can put a CDN in front of it to make the performance good for users in different geographic regions. Although maybe this is not super important because latency is not a big factor with the video. More than that, yeah, because it's a few big files instead of a lot of small requests. This API, in order to store information about for the API to handle things like searches, you might have, it really depends on what scale we want to go with this, but for a small service, you might have this just connected to some kind of SQL database. And then we're going to have a master, and we'll have some replicas. I decided to use SQL just as a default option here because I don't anticipate there being a lot of writes. I mean, if you actually are at the scale of YouTube, there would be a lot of writes, so maybe you would need to switch this from SQL to another kind of database. An alternative here might be to, if you want to make it more scalable, you could use, like let's say, Cassandra, or really any NoSQL database. You could use Mongo, you could use DynamoDB on AWS, and this is going to store information about this is going to store things like comments, titles, users, and you might also have something like Elasticsearch, which stores the text of titles for searching. But this maybe is not the best solution. So what this doesn't give you, this will tell you what matches, and it'll prioritize them in terms of how well the text match is, but it doesn't let you customize the results based on like what the best videos are. So in other words, if you want to rank the videos and provide search results that are very that give back the best results, you might actually store, instead of having this Elasticsearch here, you might also store like the recommendations for each search term. Sorry, it's really sloppy. So let's just say search results. Like you would ahead of time compute what the search results should be for different keywords, and you could store those in this Cassandra database. And in order to do that calculation offline, here you'd have some kind of let's say Hadoop cluster. So this would be a bunch of nodes that stored all the data about user clicks and whatnot, and periodically would recompute the the optimal search results for all the different popular searches. Let's see. So you might have a queue up here, which would be, I'm gonna call this the event queue, and you would queue up things the users did, like things they clicked on, searches that were made, stuff like that, so that those could be fed into this Hadoop file system. And later on, those would be processed. Those would be included in the processing that determines the recommendations. But this is happening, like this processing here is happening maybe once a day, every few hours, something like that. These events are being generated constantly, and so on, right? And all of these, in the description for, let's say, this API box up here, you would say that this was load balanced globally and locally, and maybe it was implemented in Java on the Tomcat web server, for example. I'm not showing a load balancer in this picture, but you could say in the documentation for this that it's load balancers to keep it simple. It's drawn as one box, but it's actually many instances. Yeah. So the one thing that's not super well supported here is like scrubbing through videos. If you start playing a video, you don't want to just download the video and play it as it from start to finish through. Like you want to be able to skip through it even though it hasn't all downloaded yet. And so to support that, you might actually change this design to not just store video files, but instead what you're storing is, I mean, you still could use a distributed file system, but what you'd be storing would be video chunks. So you might store the video in like 5-second chunks using a certain naming scheme. And then as you scrubbed through the video, your client, regardless of what kind of client it is, would make requests to the different pieces of the video. And then you could play those back to as long as these clients were clever enough to be able to continuously make those requests and stitch them together, then you could support it. And that's what is actually happening on these front ends. Yeah, so I think that the architecture design part of it is most interesting, but you also should, as a way of explaining what this is, for example, versus what this is, you should explain that the API is. And for this, actually, the API would just be a bunch of GET requests to get different chunks of files using a simple URL naming scheme. And like here, you would have to, when you're documenting this queue, you'd have to document what the format of the messages were here. So that would give us the idea of what kinds of events are being queued and what they're used for down here. Also, this Hadoop cluster eventually would have to probably store its results in this Cassandra database. So it's kind of like a information, the writes happen mostly through this event queue. And a Hadoop cluster figures out how so this is like user behavior is written to the queue that affects that goes into a big calculation to figure out recommendations. Recommendations are written, and search results, which are kind of recommendation, are written to this database. And then here we have a lot of reads. This database. You also have things like comments and titles and users. If you have users creating new videos and new users signing up and stuff like that, that stuff would also be written directly to the database without going through the queue, obviously. But this is mostly reads. All right, so I hope that got you thinking. Which part of that didn't make sense? All right, so now go out and create YouTube, right? Now, I mean, when YouTube was originally developed, interestingly, a lot of these components were not necessarily available. Like these days, it's pretty easy to build something like YouTube. But when YouTube was originally developed, it was much harder. Like the libraries up on the front end for doing video playing using chunks of files would have had to have been built from scratch. Distributed file systems you might have had to build your distributed file system and your distributed database from scratch. That's kind of like what Google did with Bigtable and what Amazon did with DynamoDB back in the early days. But now we have that kind of, these generic building blocks are available. Same thing with these queues. This queue is a big distributed message queue. So it handles, there might be, in a big service, there could be 1,000 copies, let's say, of this API server, and they're all writing new messages. They're all writing user behavior information to this queue. So this queue is actually a big distributed system. And yeah, and again, and this could be something like Kafka or ActiveMQ or RabbitMQ or SQS. Yeah. All right. Question from David: would you still use an event queue in Hadoop cluster even in the less scalable version that uses a SQL database instead of Cassandra? No. In a simpler version, what I would probably do is I would have this kind of design, and I might write some basic information about user behavior directly to the SQL database, or I might not. And I might handle searches. I might handle searches using a simple combination of like, does the text match? And how many views does this video have? So I might return the most popular video that has matching words from what you searched. That would work. It would, but I'm sure you realize the way that YouTube is really sophisticated in recommending videos that pinpoint exactly what you might want to see, and they recommend videos to you even if you're not searching, right? So just based on your past browsing behavior, they're giving you recommendations. I don't have a way to do that in this design, to give unprompted recommendations and to model the users, except you could still recommend videos, for example, in a very simple system by just looking in the database for, what are the videos that are most popular over all time, and what are the videos that are most popular in the past day, and you could subtract from those the videos that you've already seen. You could keep track of what videos a particular user has seen just for the purpose of helping those recommendations in a very simple way. Let me go to the next question from Piyush. I believe the next question is, wouldn't storing the best search results for every arbitrary search be memory intensive? If yes, how can we tackle that? And how does Hadoop calculate the best search result? So let me go back to the original design. So yes, it's true that storing all of the search results here takes up a lot of space, but not in a big system. So if you consider YouTube, right? The amount of data that they are storing in the files here is huge, like petabytes of data. How many different search terms do you think there really are? I know it seems like there's an arbitrary number of search terms that are possible, but if you were to actually look at the searches that people do on YouTube, and if you were to break them into components, like if someone does a really long search term, you might break it into individual words or phrases. If you break them down like that, I mean, they're only about 30,000 words in the English language, and they're only about 10,000 or 5,000 words that are commonly used. And even if you include brand names and names of people, the common searches probably only have about 100,000 unique words to cover 99.99% of all searches. So I would say when you're storing search results here, you're not storing every possible search result that's ever going to happen, but you're going to store you're going to essentially pre-cache the search results for the top 99% or 99.9 or 99.99% of search results. And this actually, that's just text, right? You have the search query terms, and then you have like a list of a few video IDs. All right, so you can store these search results on your laptop computer. You know, we're talking, and that's nothing in terms of capacity for a huge system like YouTube. So you could even cache these search results here in the front end. Even you don't even need to. You could use, for example, just to show how flexible these designs are. You could have a Redis cache here. So this is like this is a look-aside cache, meaning that when the API might get search results, and then it would store them. It could store them in memory for future use, so that it doesn't have to use the big database. It's optional. You don't have to design it that way. The second part of your question is how Hadoop calculates the best search results. So, I mean, the best search results that's kind of the way you solve that problem is by thinking about it like mathematically, and you come up with a mathematical formulation for what the ideal search result is using certain criteria, like the number of views a video has, and incorporating all the views, all the combinations of users and views that they made. You also can formulate this as a machine learning problem, like given a certain view history, let me try to predict the next video that you'll watch, right? So you could take a bunch of what sequence of videos users have watched, right? And you can set some of those aside as training, or you can use all of them as training. Set some of them aside as training, and try to fit a model that best predicts what video you're going to watch next. So there are a ton of different ways of doing this, of doing the recommendation calculation. Maybe I'll try to give one concrete example. The best example I know of for a big distributed calculation for a kind of recommendation system is PageRank for Google search. Maybe I'll present that later on. So I haven't talked about Hadoop and MapReduce. I'll have a lecture that covers that to some extent, not in a ton of detail, but a little bit. So don't worry too much if this is unclear. Just think of this as a platform for doing calculations that involve more data than can fit on one machine, and where we need to combine results. We need to do a ton of calculation across that big data set and eventually come up with some answer that's probably going to be a huge amount of data. So that's different. All the scalability that we've done up here has been about handling like a million different little requests in a minute or a day or something like that. So the scaling that's happening up here is actually kind of trivial compared to the scaling that needs to happen back here, because up here we just need to divide the system to do a lot of the same thing over and over again in parallel. Like every request that comes in only requires a little bit of work, but we have a lot of those requests to handle, and they need to somehow be coordinated by working off the same data. Like that's not totally trivial to get the databases synchronized. But back here, we're solving a much more challenging scaling problem, which is to do one calculation that involves all the users and all the users' data across the whole system. Okay.
Here a student asked a question about how new videos would be found in search results, and specifically how the text in the video could be represented in such a way to match search results. We saw in the homework for this class that Elasticsearch has full text search capabilities built in, and we use that to find news articles by searching for any of the text in the news article. Now, thinking about videos, if we're storing a description of the videos, let's say in Cassandra, a more general NoSQL database, is there any way to get that same full text search capabilities?
Cassandra does not have the same full text search that Elasticsearch has. Now, if you want that functionality, you can use Elasticsearch. So that's one of the reasons why I included Elasticsearch down here in the original design. You might want to have both Elasticsearch and Cassandra because Elasticsearch gives you some really nice full text search built automatically. However, you also can build something like Elasticsearch from scratch inside Cassandra by building an inverted index, which I mentioned in passing, very quickly in one of the lectures. But anyway, so Cassandra gives you a 2D key value store. So you have a key that goes to a set of columns and values. And you have, this is key 1, you have key 2, and so on, right? So if you want to handle a full text search in Cassandra, you can store two kinds of things. So first of all, you store the documents. You have, let's say, document 245 is, has a title and it has some text. And this text is very long, right? So if you just store this kind of data in Cassandra, the only way you can find this is by having the key 245 or by scanning through every single document in the database and looking at the contents here to find a match, right? You don't want to do that. It's very slow. But to support, Elasticsearch automatically does this thing, which is building an inverted index. So if you have a second kind of, you might call these your D keys, D for document. You might also have your W keys. So you might have W hello. This is the key for the word hello. And this maps to 245 and sorry, I guess this is a list. 245 and 3 and 478 and so on, right? There's a list of, let's say, 5 or 6 documents that have the word hello. So that the text in here might have said hello. That's what I'm showing here. I have to take every single word in this document and add this number 245 underneath the key for that word. So if the word world is also in there, right? I need to make sure I add 245 to the end of the list of the list of documents that have this word world, right? So now if I want to support a search, I go through and do this for every single word. There might be 3,000 words in here. That means I'm going to add 245 to the document list of 3,000 different keys for all those different words. The benefit of doing this, it's a lot of work, extra work that we have to do. And if you're doing this manually with Cassandra or DynamoDB or Mongo might have some of this built in actually, but the point of doing this is that later on, if I want to do a search for hello and world, I want to find all the documents that have those two words. I don't have to scan through every document. I just build up these two keys, get the results, and then do an intersection of these two, and that gives me the documents, right? So there's a lot of work done ahead of time. There's a lot of indexing. This is indexing work that you do when you insert the document. You have to add to these this is an inverted index. Yeah, here. But these are, yeah. I have documents and I have the words stored in the key value store. I don't remember if that was your entire question.
Now there's a follow-up question from the student asking about when a new video is added, how is that video added to search results? If we're computing and storing search results ahead of time, then new videos would not be available in those search results. Yeah, so if you have anytime you have a system that is
anytime you have a recommendation system, whether it's for videos or products or whatever, you always have to include some kind of randomization to seed results, right? Like if I'm a new user on YouTube and I post a video, YouTube has two choices. Either they can never show the video to anyone, or they can only show the video to users if they search for a text that's in my title. And for some reason, I'm the only video that has, I'm one of the only a few videos that has this word in the title. That's very rare. So instead, what they'll probably do is they want to know the quality of my video, basically, right? Usually the way they measure the quality of content is to see how popular it is. So popularity is a proxy for quality, but when something is new, it has zero popularity, right? And that doesn't really give us an answer of the quality. So they kind of test the quality of the content by randomly giving it to users, and then kind of seeing what the user's reaction is. So does the user stay and watch the whole video, or do they leave immediately, right? That gives YouTube a signal about what quality this video is compared to other videos that have the same text in the title. Like if I post a new database lecture on YouTube, there are thousands of other database lectures that have more views than mine. But I don't know for sure, but what YouTube might want to do is to provide my database video to some of the users who search for databases. Even though there are many other videos that are more popular and probably are better, there's a chance that my video is better, and they want to test that, so they provide it to some users and see how engaged the users are with this video. Does the user continue to the end of the video? Does the user click on my next video from me? That would be a strong indication that the popularity, that the quality of this video is high. So to build a real system, you need a somewhat complex formula and like strategy for ranking videos and building search results. You cannot just rely entirely on popularity for exactly the reason that you mentioned. So it's a lot of like manual tweaking, I guess, and like having two different ways of providing search results and mixing them together. So for the next question, I think, is on video upload. To upload videos, what I would probably do is have an endpoint here. There'd be a post on this API here that would accept the file data in a REST request. And then, so there would have to be, that brings up the point that there has to be a connection here to S3. So the way the video files are not just like here indefinitely, they have to be stored. And actually, probably you would need a pipeline of some kind. So you might need to store the files in some kind of S3 temporary bucket, and you might also need to put a message. Sorry, this is covered up. How do I make this? Let me make this smaller here. So here you might have a queue of like, this is an encoding queue. So here we might have a description of a video that is stored in this database temporarily that needs to be re-encoded to finally be stored in S3. So here I have an encoder. So this is a program that takes a video file that was provided by the customer and translates it into a format that is appropriate. Because remember, the user is going to be maybe providing a video that they shot on their iPhone. It's one big video. It's maybe high quality. What's stored here is, so we have time chunks, and we have different quality levels. So for every file that is uploaded, we might generate, 200 files, maybe 2 or 3 different quality levels, and then we're breaking it up for every 5 seconds into a different chunk, okay? And that work would be done here, and it's decoupled from the API because this is going to take a long time to run. So actually, that's a very good point. This is a significant and important part of this architecture. Okay, a question from Yuki about Hadoop. question is, does it not only store the data in a distributed way like a database, but also have functionality for analyzing data? Yes, that is the key thing about Hadoop and Spark and similar platforms, is that these are big data processing platforms. And in order to actually do a good job to efficiently computing something on a large amount of data, you cannot use this design that separates databases and compute, because you'd end up transferring data back and forth all the time. Instead, you have a combination of a distributed database and distributed computing platform, where you write a code for analysis the code gets sent to all the database nodes, essentially. Except they're not just database nodes, they're database nodes that are nodes that are capable of running arbitrary code. And they run that code on the piece of the data that is stored locally, and they also have a runtime system that shares results when they need to be shared. There are temporary results that have to be shared and redistributed. So it's kind of a whole complex platform for doing analysis that you write. The way you write it has to fit with the rules of MapReduce for Hadoop, which we'll talk about later. So you have to write it in a specific way to get it to run on this cluster. And then, but yeah, like you were asking, the data and the computation this is both a distributed database and a distributed computing platform at the same time.